So let us say you tell a restaurant assistant, find me a table for Friday at 7. You pause for 1 second. Before you can say, actually, Saturday, the agent jumps in. Sure, I can help with Friday. You correct it. No, no, Saturday. But it just keeps talking. The language model may understand every word and find the perfect restaurant, but the conversation is already broken. It spoke before you finished, then refused to stop when you started again. This is not mainly an intelligence problem. So, what failed? Was the model slow, or did the application simply not know whose turn it was? Both can matter, but the second one is the part people miss. A voice agent is not a chatbot with one microphone and one speaker attached. It is a real time turn taking system. So, first, the obvious version. Your microphone sends small audio chunks into speech to text or STT, which converts the voice into words. Those words go to the language model. Its answer goes into text to speech or TTS, which converts the text back into audio. Audio in, text in the middle, audio out. This is a cascaded pipeline. One stage passes its result to the next. It is modular and we can inspect each step when something goes wrong. Now, build it in the most naive way. Wait for the user, then the full transcript, then the full model answer, then the full generated audio. Only after all of that, press play. Every box waits for the previous box to finish. So, that silence is not one delay, it is turn detection, network transcription, the model's first word, the speech generator's first audio, and the playback buffer, a small cue which keeps the sound from breaking. So, when somebody tells my voice agent is slow because the LLM is slow, maybe, but not necessarily. Voice latency is a chain of waits. If we optimize only the model while all the other boxes keep waiting, the call can still feel exactly the same. Now, think about the same pipeline properly. Does text to speech need the model's entire 5 paragraph answer before it can speak the first sentence? No. Does speech to text need the complete recording before it can show the first few words? Again, no. So, why are we waiting for full completion at every stage? We can stream it while you are speaking. STT sends partial transcripts a few words at a time. Once the system has enough stable input and believes your turn is ending, the model can begin. The moment the model produces a useful phrase, that phrase can move into TTS. And TTS can start returning audio while the model is still writing what comes later. Now, the machine is moving continuously. The transcript is growing, model tokens are coming out, audio chunks are being generated, and the speaker begins playing the first chunk while the rest of the answer does not even exist yet. That is the important part. Start the next stage before the previous stage is completely done. But the text chunk cannot be arbitrarily small. Send every few tokens to speech generation and the voice may sound broken because it does not know where the sentence is going. Wait for a full paragraph and the delay comes back. So, one common approach is to buffer around a phrase or a sentence, enough context to sound natural, but not enough to create a long pause. I want to be precise here. This does not mean every box runs independently in parallel. TTS still needs some text, right? The model still needs enough of the user's request. The stages depend on each other, but partial results allow them to overlap. That difference matters. And early work can be wrong. A streaming transcript may first hear one word and correct it when more audio arrives. Or we may start generating, then discover the user was only pausing and has continued the sentence. Faster response, but sometimes we throw the early work away. That is the trade off. So, the useful latency number is not how long did the full response take. For the person on the call, it is closer to this. From my last sound, how long until I hear the agent's first useful sound? Streaming reduces that gap. But now we have a more difficult question. When exactly was my last sound actually the end of my turn? The simplest signal is voice activity detection or VAD. It looks at the incoming audio and estimates, is there speech right now or is this silence and background noise? When speech stops, we start a timer. If the silence lasts long enough, we mark the user's turn as complete. This works, but the timer is a compromise. Make it very short and the agent responds quickly but it keeps cutting people off when they pause to think. Make it long, and the cut-offs reduce. But after a simple yes, everybody sits in dead air waiting for the timer, fast or patient. A fixed number cannot be both for every sentence. Look at our call. Find me a table for Friday at 7. The waveform went quiet. VAD did its job correctly. But did the sentence feel complete? Not really. The words and the tone both tell us that something may still be coming. Silence was evidence. It was not permission to take the turn. So, better systems may add another decision on top, depending on the implementation. They can use the transcript, conversation context, or audio cues such as intonation and rhythm to estimate whether the thought is complete. The exact approach changes, but the idea is durable. Do not ask only, did sound stop? Ask, does this sound like the person is done? Humans do this almost without noticing. In studies across languages, the common gap between people's turns is measured in hundreds of milliseconds, not seconds. That is too quick to hear the full stop. Begin thinking from zero, prepare a sentence, and then speak. We are predicting the end while we are still listening. The application therefore tracks two things at once. On the input side, listening, maybe ending, turn committed. On the output side, idle, generating, playing, cancelled. Above both is one decision. Does the floor belong to the user, the agent, or is it still uncertain? That is how the agent can speak and keep listening at the same time. With that fixed, our agent waits through Friday at 7 and here's actually Saturday as part of the same turn. Good. But now let us say it has started speaking and we genuinely want it to stop. How does the turn move back? When the user starts speaking while the agent is speaking, that is usually called barge-in. Plain meaning, you take the floor before the other side finishes. A natural voice agent has to allow this because a voice that cannot be interrupted feels less like a conversation and more like an audio recording. The first job is obvious. Stop the sound immediately. Not after the current sentence, not after the audio queue becomes empty. The application has to stop playback and clear the chunks which were already generated but not yet played. But if we stop only the speaker, the model and text to speech may continue working silently in the background. More tokens, more audio, more cost, and possibly more state we do not need. So, where the system supports it, we cancel the active response or at least discard everything coming from that old response. Then comes the subtle bug. Let us say the model generated I found a table for Saturday at 7 and it has outdoor seating, but playback stopped after I found a table for Saturday. What should the model's conversation context contain? Only the portion the system knows it played, not everything it generated. If we keep the longer generated sentence, the next model call believes it already mentioned 7 and the outdoor seating, but playback never reached that part. Now, the model and the human continue from two different conversations. So, the machine continues from the conversation the user experienced, not the longer one sitting inside the server. That is a proper interruption. Stop the sound, stop the work, repair the history. It is a cancellation traveling backwards through the whole pipeline, not one pass button on the speaker. And even here, every bit of detected speech is not a real interruption. You may say, while listening, there may be a cough or somebody speaking in the background. The microphone can even capture the agent's own speaker output. So the audio path may use echo cancellation to reduce that sound before turn detection sees it. Otherwise, the agent can literally interrupt itself. So, interruption handling also uses duration, words, or acoustic evidence to ask, is this person trying to take the turn or only acknowledging me? If it was a false alarm, the agent may resume. Same waveform signal, but one more decision about ownership. Now, you may be thinking, this STT to LLM to TTS chain already sounds old. Some real time systems expose one speech to speech engine to the application. We send audio in and receive audio out without wiring separate STT, LLM, and TTS services ourselves. They may still provide transcripts as well, but text is no longer the mandatory bridge between every stage. So, did we solve the whole thing? We removed some handoffs, which can reduce latency, and the model has access to signals that plain text loses. Tone, emphasis, rhythm, whether somebody sounds uncertain. It may use those signals while understanding and producing speech, which can make the conversation feel more natural. But the modular pipeline gives us a transcript at every step, lets us replace one provider without replacing everything, and makes failures easier to inspect. With direct speech to speech, some of that control and visibility becomes harder. I do not think one architecture is correct for every product. It depends on what we are building. The thing is, look at what did not disappear. We still have live audio coming over the network. We still have to decide when the user finished. We still buffer outgoing sound. We still need to notice an interruption, stop playback, cancel the response, and keep the session history aligned with what user heard. So, speech to speech changes the engine inside the voice agent. It does not remove the conversation control system around it. This is why I would not define a voice agent by the three boxes. The difficult part is not making the AI speak, it is deciding when it should stop. So let us replay the call. Find me a table for Friday at 7. The audio becomes quiet, but the turn remains uncertain. Actually, Saturday. Now it is committed. The response starts streaming, and we hear the first useful words without waiting for the full answer. The agent says, I found a table for Saturday at 7. And we say, no, make it 8. Incoming speech takes the floor. Playback stops. Queued audio clears, the response is cancelled, and the unplayed tail leaves the model's context. Both sides continue from the same conversation. That is the mission. Listen, decide whether the turn ended, stream the response, and speak while still listening. If the person takes the floor, yield, cancel, repair, and continue. The language model is one part inside that loop. So, success is not only low latency, it is low latency without premature turns, false interruptions, or model context containing audio the system never played. A fast wrong turn is not good latency. So, at high level, a voice agent is not a chatbot with speech added. It is a real time turn taking system which must continuously decide who owns the conversation. The answer can be intelligent, but if that ownership is wrong, the whole product still feels broken. The stream, turn detector, buffers, and cancellation path, that is where the conversation actually lives. If this kind of systems view help you understand AI without the hype, subscribe. We'll keep opening these applications and looking at what actually makes them work.